Welcome to solverfy.
6.47. So we want to use the table that's given earlier in the problem set of the periods and mean orbital distances of the 4 largest moons of Jupiter. And so we want to take Kepler's law in this form and show that if we plot the logarithm of the period of each moon against the logarithm of its mean orbital distance, we want to show that this will give us a straight line, and then talk about what the slope and y-intercept of that line mean, or are at least. And then we want to plot this and figure out the mass of Jupiter based on that. So to begin with, we just take the logarithm of both sides here. Where m sub capital J is the mass of Jupiter. Oh, wait, no, we're not on part B yet. So, just using the properties of logarithms, we'll see that this is 2 times log t. And this is the logarithm of a product, which is going to be the sum of the logarithms. And then also we'll get a 3 down from our log r cubed. So we have 3 log r plus the log of 4 pi squared over gmj. And then if we just divide both sides by 2, we get log t, which is our sort of our y, equals 3/2 log r. So this is going to be our slope times x. So this is the slope of the line will be 3/2 plus 1/2 times the log of 4 pi squared over gmj. So this is good. So if we plot log of t versus log of r, we know what the slope should be. And then we also know that we can find the mass of Jupiter from the y-intercept. So for part B, I'll just sketch what this ends up looking like. Doing this yourself, you want to actually plot it, which you can do easily enough using a spreadsheet or something, or however you like to make plots of things. But we'll have our 4 moons here and their orbital distances versus their periods. And since the data in the table are fairly precise, they end up basically all being on this best fit line. And so the best fit line is 1.5, which you can, I don't know if you can set that as a constraint in a spreadsheet, but with other fitting methods you can. Minus 7.76. So this is the best fit line you should get. So 1/2 log of 4 pi squared over g mj equals the intercept. So the mass of Jupiter, then, you just solve this. 4 pi squared over g times 10 to the 2b. Now, this assumes that you've taken the logarithms to the base 10, which is what's usual for making log-log plots. If you took the natural logarithms, this should be an e and so forth. And also you would get a different value for the intercept then, though, so just be careful with that. And so putting in the numbers we have here, 10 to the 27th kilograms. And this ends up actually, as you would hope, being quite close to the actual mass of Jupiter, which you can see is quite large, which, again, you would expect because Jupiter is a very large planet.